Let's see how the motor is built. There are two coils of 250 turns of magnet wire each. We use magnet wire of size 26 AWG, and the coils are over 2 screws with its nut and washer, and there is an electrolytic capacitor. The connections we will see in a moment, and for power we use a 6-volt transformer. This is alternating current. The rotor is a can of aluminum. I used the can from a big capacitor like this, and it rests on the tip of a needle with a heavy base so that it can rotate freely and we can move it and adjust the distance. Let's see the connection. This is the AC input, and this coil is connected one of its sides to the AC and the other side to the other AC terminal. The second coil has one side to one terminal of the AC, and the other side goes through a capacitor and then to the AC terminal. That is, while the first coil is connected directly to the AC, the second coil has a capacitor in series with the AC input. And now let's see how the motor works. What is the principle of operations? The coils are fed with alternating current, so they generate a magnetic field that increases and decreases continuously. But one of the coils is connected through a capacitor to the alternating current. The effect of a capacitor is to lag the current from the voltage in the coil. So the two magnetic fields of the coils are not in phase. When this magnetic field is increasing, the magnetic field from the other coil is decreasing, and vice versa. Okay, on the other hand, when a magnetic field cuts a conductor, the rotor is made of aluminum, that is a conductor, a current is induced on the conductor. So we have currents here in the aluminum can, and these currents in turn generate its own magnetic field, and because of Lenz's law, the magnetic field in the can is of the same sign of the magnetic field in the coil, and they repel each other. However, because the fields of the coils are not in balance, this generates a difference in force between the two coils in the can, and this difference generates a torque that makes the rotor rotate. The rotor must be as close as possible to the coils in order for the induction to take place in an effective way. I'm going to connect the coils, and we can see that there is no movement in the rotor, but I'm going to push it close to the coils, and we see how the rotor starts to move. Let's move it closer. And closer. If you want the rotor to move in the other direction, you only need to invert the connections of one of the coils. Hope you liked the video. Thanks for watching.